technical problems are solved. So let me start by introducing our group at the Max Planck Institute for Solid State Research in Stuttgart, in the south of Germany. In particular, I like to introduce this group of bright PhD students, which actually did most of the work I'm going to present today. So outline of my talk is short and simple, so I also like to focus on lanthanum nickelate superlattices as Marta did, slightly different. I will explain this in the following. And using resonant X-ray scattering, we investigated the orbital polarization, the magnetism, and charge order in these lanthanum nickelate-based superlattices, and also in praseodymium nickelate heterostructures, where I'm only giving a short summary here. So I don't need to give such a broad introduction, because the previous speakers already did very well. So we are interested in heterostructures of transition metal oxides, and due to the strong electron-electron polarization in these class of materials, the properties are largely defined by the local degrees of freedom, that is spin, charge, orbital, and lattice degrees of freedoms. A very common structure, as we already heard, the perovskite structures, which have an ideally cubic structure with A cation in the center of the cube, and the B cation at the corner, surrounded by by 6 oxygen, forming an octahedron. Depending on the size of the rarest ion, actually it is found that most of these transition metal oxides crystallize in distorted structures, and in good approximation, these distortions can be explained by tilts and rotation of the octahedra around the crystal axis. So we are interested in what's happening at interfaces, and we already heard interesting examples of charge transfer which can occur at interfaces, and magnetism, and also orbital reconstructions are possible depending on what kind of materials you put together. A challenge for these oxide heterostructures is not only the growth of these materials, but also for the experimental investigations, because we have to deal with ultra-thin layers on a nanometer scale. That's where the interesting phenomena occur, and at interfaces which are even on a sub-nanometer scale, very often the layers of interest are buried, and we can have, as Marta nicely presented in her talk, have multi-layers with multiple electronically or magnetically active elements. So we are using X-ray absorption and resonant scattering, mostly in the soft X-ray range, because we are interested in the valence state of the 3D transition metal ions. So we are mostly focusing on the L edges, which then the absorption process is then by exciting a 2p core hole with the open 3D shell. So the fine structure of these absorption spectra can give you very valuable information on first of all, the energy is characteristic for the particular elements. So by tuning the energy to the certain edge, you can study them in an elemental sensitive fashion. The fine structure is very characteristic for the valence state, chemical surrounding, and crystal field. And by using the polarization of the incoming light, either being linearly or circularly polarized, you can study the X-ray dichroism, which gives you also important information on the orbital polarization. I will come to this later. The antiferromagnetism, or also the ferromagnetic spin and orbital moment, can be deduced by so-called XMCD measurements. So that is where actually the scattering tensor, the X-ray absorption, is proportional to the scattering tensor, and in this case we are probing non-cubic scattering tensors. The resonant scattering is closely related. It's a photon in, photon out process due to the same absorption adds. And here the phase factor enters into modulates the intensity, and from this you can study spin and charge and orbital order also in an element sensitive fashion. So our model system, as already introduced by Marta, are the rare earth nickelates. We have seen this phase diagram already, so I don't need to tell so much about it. So far we have focused on heterostructures based on this lanthanum, praseodymium, neodymium nickelates. So more on the itinerant side of the phase diagram, with the lanthanum being the member of the family which is metallic and paramagnetic down to lowest temperatures. The neodymium and praseodymium actually show Niel and metal insulator transitions around 130 and 200K. So formally, the nickel is in a 3+ valence states, and due to the crystal field, these atomic 3D states are split into a T2G and an EG manifold, and the 7th electron is occupying the EG, the open EG shell. We have, also in comparison to what Marta presented, essentially looked into multilayers and heterostructures composed of the rare earth nickelate with a large band gap insulator. So our motivation was to modify the electronic properties through either the biaxial strain induced by the substrate and to study the effect of confinement when reducing the layer thickness between these two band insulators. There was a series of theoretical work on this kind of heterostructures, and they proposed orbital order and possible superconductivity in these samples. So as I said, that was our motivation to grow these superlattices, so stacks of lanthanum nickelate and the large bandgap insulator, and we varied the chemical composition of these large bandgap insulators to be lanthanum aluminate, lanthanum gallate, dysprosium scandate, gadolinium scandate, and we looked at the function of the layer thickness of the lanthanum nickelate and varied it between 1 and 4 perovskite unit cells. So the samples were grown by two techniques, molecular beam epitaxy and PLD. Actually, the first samples were grown by PLD, but we put a lot of effort in order to improve the sample quality. You can see 2 TM images of the samples by also growing these superlattices by MBE. So although the interfacial sharpness or roughness is improved in these MBE samples, the physical properties for samples grown by these two methods are essentially the same. So, having these nickelate, lanthanum nickelate multilayers with different insulating material, band insulators, are grown on different substrates. We looked at the linear dichroism in order to study the orbital polarization as a function of strain and insulating material. Here you can see from compressive strain going up to a large tensile strain, and by analyzing these data quantitatively by making use of the sum rule, which relates, actually something is wrong here, but the ratio of folds in the 3 squared orbital to the ratio of folds in the planar orbital to the intensity measured with V and X polarized light. And we can get a quantitative determination of orbital polarization as a function of strain induced by the substrate. And also by modeling these data with a simple cluster model, we extracted the splitting of the EG level, which actually linearly increases, so is negative for compressive strain as expected, then crosses 0 and increases almost, or a good approximation, linearly with strain. So, in order to get even more deeper insight to the effects of confinement and chemistry across the interface, and also to some approximation to disentangle them, we introduced a method, an analysis method of resonant reflectometry measured with linear polarized light, which is called orbital reflectometry. So the idea is we have superlattices with a 4-unit cell thick stack of lanthanum nickelate. So we can separate the interfacial layer from the inner layers, and by doing reflectometry at the OO2 superlattice reflection, this is particularly sensitive to the difference in scattering factors between these layers A and B. We can determine layer-resolved orbital polarization profiles. So this is summarized in this graph here. You can see the orbital polarization as defined by the difference in x squared minus y squared minus 3z squared occupation in percentage as a function of the in-plane lattice parameter measured by x and b for the different samples. And the triangles note the orbital polarization of the inner layer, which we believe is mostly affected by the strain. So both layers are in the same way affected by the strain, but in addition, these interfacial layers have the effect of confinement due to this insulating material and the different chemistry across this interface. So you see, in good approximation, we find a linear dependence for the triangles, for the effect of strain, if you want. And it goes, so we find orbital, so maybe up to 20% or even 25 in total, while the effect of the interfaces, that's the diamond symbols here, falls into a comparatively narrow window of a few percent. So from this we concluded that strain is the most effective control parameter, and that was also found in DMST calculations in the group of Antoine George in Paris. Here again you see that here's plotted the whole ratio as a function of strain, and you see these red crosses fit very nice to triangle again our data from this graph. In a second study, we looked into magnetism. So Marta already have shown these data from muon spin rotation, where we found first evidence for magnetic order in lanthanum nickelate when being 2 unit cells thick. So we used resonant X-ray scattering to study the ordering vector and its energy dependence in more detail, and that is what we found. So this is the quarter L in this case, because in case it's rather raw, elongated. No coupling between or small coupling, no coupling between neighboring lanthanum nickelate layers. Peak measured on resonant, and as a function of thickness. So red is a sample with 2 unit cells of lanthanum nickelate, blue is 4 unit cells, and you clearly see that we only find a magnetic peak for 2 unit cells. And this is clearly resonating at the nickel L edge, showing that it's on nickel. So by looking at the scattered intensity, so the sigma or the phi ratio of the scattered intensity when turning the sample around this quarter vector, so we started taking the azimuthal dependence of the scattered intensity. We found differences as a function of strain, essentially, or if of orbital occupation. So for tensile strained samples, we found that the moments of the spin spiral point more out of plane, while for compressive strain they are in the plane of the sample. And if we have a confined situation under compressive strain where things kind of cancel, we find them in the 90-degree so at 45 degrees to the z-axis and with 90-degree angles between these moments. So from this, we concluded that the occupation of the d orbitals is then controlled by the magnetocrystalline ionized tree-wireless spin-orbit coupling. So, but now we are left with the question, okay, so we have magnetic lanthanum nickelate. When making a 2-unit cell 6, it's even antiferromagnetic ordered with the same wave vector as found in the bulk materials. Is it just the case that kind of we have changed the lanthanum nickelate in a sense that we made it more like the charge ordered and magnetically ordered raw earth nickelates with smaller raw earth pions? So in the case of, for example, neodymium nickelate, there was also resonant X-ray scattering study by Stout and Scaglioli at that time, and they found that there is a charge order at a checkerboard like charge order with order vector half. So we did this experiment also for our samples. Unfortunately, this vector is, you cannot reach these Q vectors at energies in the soft X-ray range, so you cannot perform these experiments at the nickel L edge, but you can go to the K edge, and that was also done with this neodymium. We also measured a neodymium reference film and the 2x2 2-unit cell lanthanum nickelate aluminate superlattice. And indeed, for the neodymium nickelate, we see a strong increase. So this is the energy dependent of the scattered intensity, so across the nickel K edge at the half. Reflection, and when entering the charge ordered state, we find a strong increase of the signal. Nevertheless, we also have a modulation and energy dependence at room temperature, and that was pretty puzzling. So it took really 1.5 years to analyze this data, because we first needed to understand where these non-trivial energy dependence came from. For the lanthanum nickelate aluminate superlattices, we have essentially no temperature dependence, but we also see these energy dependence of the scattered intensity. So to understand this room temperature wiggles better, we performed DFT calculations to obtain the atomic positions at room temp, at the low and the high temperature phase, at room temperature and in the charge ordered phase, in case of neodymium nickelate, and then calculated the scattering factors by scaling it to the 4p density of states, and then calculated the energy dependent of the scattering. And the results you can see here by these black curves. We by only considering structural distortions due to the tilt and rotation of the octahedron, which are reduced to the epitaxy with the substrate in these neodymium nickelate layers, we can reproduce the scattered intensity very well. However, at low temperatures, where the system goes into a charge, it's charge ordered, it's not enough to describe the observed energy dependence, and here we need to consider bond disproportionation plus the tilt. In case of the lanthanum nickelate superlattice, we can describe the full temperature dependence and also the energy dependence at different crew or for different polarizations by only taking into account the tilts. And from these results, we could obtain an upper bound for the bond disproportionation in our lanthanum nickelate aluminate superlattices, and what we found is that it's smaller than 0.01 angstrom. In comparison, the neodymium nickelate, that is also in good agreement with results from polycrystalline samples, has a bond disproportionation which is about 7 to 8 times larger than this So altogether, we concluded that we actually found a new phase without the bulk analog and this 2-unit cell thick lanthanum nickelate multilayers, which might best described by a spin density wave. So this is kind of a result of all our studies. So if you make lanthanum nickelate on different strain and confine it, you will find this low temperature phase independent of the sign of strain. This is different if you look at the same kind of qualitative phase diagram for praseodymium nickelate-based heterostructures. Here it appears that depending on the sign of strain, so for compressive strain, you can compress the metal insulator transition, which is observed in bulk. While for tensile strain, it looks bulky from temperature and then if you confine, if you start with a compressively strained praseodymium nickelate and confine it at a critical thickness of 4-unit cells, we again find our spin density wave. So a metallic spin spiral with quarter ordering again. While in the case of the tensile strained lanthanum nickelate, the effective confinement is only marginal. The temperatures depend a little bit. The transition temperatures depend a little bit on the thickness and the sign of strain or the amount of tensile strain. So from these results, I may have to say, so also we did Raman studies on this, and we clearly see a structural change for samples grown under tensile constraints. So we observe more phonon modes in this area of the phase diagram compared to the one in compressive strain, which then also changes as a function of temperature for the tensile strain and shows effectively no temperature dependence for the compressively strained praseodymium nickelate heterostructures. And taking all this together, we concluded that the structural distortions possibly play the crucial role in determining the physical properties of these praseodymium nickelates, and that's something we are further studying also by non-resonant X-ray diffraction. So to summarize my talk, actually I did this in the 2 previous slides. So for lanthanum nickelate-based superlattices independent of the sign of strain induced by the substrate, we found a dimensionally driven or induced spin density wave with a critical thickness of 2-unit cells. While in the case for praseodymium nickelate based superlattice, the compressive strain suppresses spin and charge order, but reducing the layer thickness can induce a spin density wave when going below 4-unit cells. Before I come to the end, I like to acknowledge my collaboration. So this is a project between many people, and I'm very grateful for this collaboration, and thank you for your attention.